Hey there! Welcome to another video. We're going to take a sidestep, but not maybe an unexpected one. You see, what we've been talking about for a lot of videos was linear equations in one variable, and then at the very end we talked about linear inequalities in one variable. Likewise, we just spent a lot of time talking about linear equations in two variables, and now we're going to talk about linear inequalities in two variables. So what these videos are going to be geared towards for the next few of them is getting us to graph systems of linear inequalities and seeing what that means. In this video, I'm going to introduce them. I want you to get a feel for what they are, how they work, and most importantly, what a solution set is. What are the solutions to linear inequalities with two variables? And the way we're going to talk about it is I'm going to reintroduce what linear equations are in two variables, and we'll talk about that. We'll talk about what the solution was and why it's not the same thing with linear inequalities, why we get a different sort of idea as representing solutions. So let's look back at linear equations. Now, we had linear equations like this, that was standard form, or like that, that's slope-intercept form, and we were very good at graphing them. Why? Why were we good at graphing them? You all know that that makes a line. You put that on a graph with an x-axis, y-axis, you get a line. But why? Why do we even want to graph that? Well, let's think about that. What we determine with linear equations is that any point, any ordered pair with an x and a y that satisfies that equation, that makes it a true statement. So on the left and the right would be the true, would create this equality. For instance, like 0, 3, the point 0, 3, x is 0, y is 3. That's a true statement. What that means is that point would be on the line that equation gives us. Well, here's what a graph is. That graph is the way that you represent all the solutions to that equation. There's no other good way to do it. So, I mean, what do you want to do? You want to list out all the points that work here? I mean, you're going to be there for an awfully long time. But because listing out all the points is impossible for us to do that. The way that we show all solutions, this is important for you to get. This is why we graphed. The way for us to show all the solutions at once of that equation is only through a listing out of all the ordered pairs or a graph. So when we graph a line, we're saying, hey, all the points that line goes through are solutions to that equation. That's what the line is. It's all the points at once. It's the entire solution set. So when you were graphing linear equations, when you were doing that whole thing, what you're doing is you're showing the solution to the line. You're showing all the points at once. That's the idea. That's what linear equations are. So our transition from linear equations, which the line is just the picture of the solution set, unless you want to spend time writing out all the points, which I know you don't, because you can't do it, it's possible, that is the picture of our solution set. It's the line. That's why we call it a linear equation, because the solution set makes a line. Now we transition to, okay, imagine we don't have an equals. Imagine we have an inequality, so less than or greater than or less than or equal to or greater than or equal to. When we replace an equals with one of those symbols, we don't get an equation, but what we get is a linear inequality in two variables. Like that. I use the same variable as a number on purpose so you can see the connection here. Well, let's talk about this. Firstly, what would a solution be? How many solutions are there? Over here, there's a lot more than one solution. In fact, there's an infinite number of ordered pairs that actually satisfy that. We're going to find the same thing here. So let's try plugging in some points, some ordered pairs, and let's see what are solutions and what are not. And the main thing I want you to distinguish is there's going to be a big difference in the picture between a line and a linear inequality. So between a linear equation and a linear inequality. Let's try a very simple one. Let's plug in 0, 0. So 0 for x, 0 for y. Remember, what we're doing here is we're testing whether an ordered pair is a solution or not, whether a point satisfies that inequality or not. If we plug in 0 for x and 0 for y, we're going to get 3 times 0 plus 5 times 0, and we're checking whether that's actually less than 15. Well, let's see, 0 is less than 15. So we get ourselves a true statement. If we get ourselves a true statement, something that's true, that's something our inequality says is true, well, that says that point satisfies that linear inequality. That's a true statement. That means this is a solution. Here's the important thing I want you to notice. If you plugged in 0, 0 here, 0 does not equal 15. So here's the big difference. Listen carefully. This is a big deal. Here's the big difference between linear equations that make lines and linear inequalities, which we're not sure what the heck they make. Well, we are, but we have to forget. So if you plug in 0, 0, the same exact point to this equation, you'll get a false statement. You'll say that that point's not on that line. But here, we plug in 0, 0, and we get a true statement with an inequality. Now notice something. That point still isn't on a line. It's not on that line. It's not on this line. However, it's still a solution. So with linear inequalities in two variables, with inequalities in general, we get a much broader range of solutions. So for instance, do you remember linear inequalities in one variable? When we had an equation, generally has one solution if it's linear with one variable. And then with inequalities, we got an entire half of a number line, or half of a number line, or in between, with systems in between. We're going somewhere with this. Inequalities generally have a much larger range of solutions. That's not even on the line, and yet it's a solution to this linear inequality. That's interesting. We'll get to what that means in just a bit. Let's try another one. So if we were to plug in 1, 2, that's 1 for x, and 2 for y. Well, that gives us 13. And again, that's a true statement. We do know that 13 is less than 15. That's true. Any point, any ordered pair that creates a true statement is going to be in the solution set. That's what happened here as well. We tested a whole bunch of points like a long time ago. Said, oh yeah, that point worked. Hey, it's in the solution set. It's on the line. Oh wait, that line is the representation of the entire solution set. All the points. Pretty cool. Now here we're starting to do the same thing. We plugged in a point, it was true, we say it's a solution. It's in the solution set, whatever that happens to be. We plugged in another point, it created a true statement. We say that this point is also a solution. That means it's in the solution set. Now, is this point on the line? No, because 3 plus 10 is still 13. 13 doesn't equal 15. It's not on the line. Same exact numbers, yet it's not a solution on the line. It is a solution in the inequality. Much larger range of scope of solutions here. Let's do one more. How about 1, 5? So 1 for x, 5 for y. We get 28. We get 28. Huh. Well, that doesn't look right to me. It doesn't look right to you. That's a false statement. That's why it doesn't look right. It'd be like doing both of these points over here and going, that doesn't work. That's right, because those points aren't on that line. The line is a representation of the solution set. We go, no, those points aren't on that. Those points are not part of the solution set. This point creates a false statement. It's saying whatever the solution set is, this one ain't part of it. So that's not a solution. Okay, I lied. One more now. So I want to show you one more thing. Let's plug in one more point. Let's plug in 0, 3. If we plug in 0, 3, that's 0 for x. That's 5 for y. And we can do this with positives and negatives. I'm just showing you some simple ones so you get the idea here. I get 15. And we look at it and we go, wait, oh, that's weird. Is that a true statement or a false statement? Well, it depends on the inequality. There are some inequalities for which that would be true, but not this one. 15 is not less than 15. That says that in this inequality, that point is not part of that solution. Now, this is a big difference between linear equations and linear inequalities. If you plug in 0, 3, I referenced it earlier, if you plug in 0 and 3 here, you're going to get a true statement. You're going to get, yes, that point is part of the solution set. That point is on the line. That point is on the thing that represents the solution set. For sure, it creates a true statement. Yet when we get to inequalities, Man, this is weird. Even the points that are on the line from where we even got this are not part of the solution set. Now, why? This is a big deal. Why does that happen? Look at your inequality. Your inequality is strictly less than. It says your left side has to have values that's smaller than your right side. Strictly, not equal to. So in this particular inequality, the points that are on the lines aren't even aren't even solutions. They're not even part of the solution set. So what in the world do linear inequalities in two variables mean then? Well, it can't mean just a line. Equations mean a line. That's the way you represent solution sets for linear equations in two variables. So it can't just mean a line. In fact, there's a lot more than one solution. In fact, none of these points that were solutions were actually on a line. They were either above that line. Listen carefully here, I'm getting to it. They were either above that line or they were below that line. In fact, that line, the line that's based on, that line, is the separator for all the points in the universe. Half of those points are going to be solutions and half of them aren't. So what the linear inequality does, linear inequality says, pretend that you have the line, the equation part, just like that. Pretend you got that. And then start testing points. Either all the points above the line are going to work, or are going to create true statements, are going to be solutions, part of the solution set. So either all the points above the line is your solution set, or all the points below the line is your solution set, not both. That's what a linear inequality does. A linear inequality is much more than one solution. So are lines, but this is much more than just a line. This is saying that line separates the plane in two. You get half a plane, like plane being the flat thing, half a plane, either the top half or the bottom half that are solution sets. So more than one solution. In fact, half of a line, half of the top half or the bottom half. That's kind of the way that I'm going to get to this next thing, what it really is. One side of a line is a solution set. That's called a half plane. So let me ask you one more question. I'll recap the whole thing and then we'll be done. It's a relatively quick video for me. So in this case, because 15 is not less than 15, this is not a solution. Now, what if I were to change one thing? What if I were to make this equal? That would still be true, that would still be true, that would still be false. But now that would be true. And here's what it is in general. So here's what the whole recap, and I'll end with that statement. Linear equations make lines because the line is the only way to represent the solution set for us. It's the only way to show all the solutions all at once. It's by graphing. We have to be able to do that. We don't have number lines anymore. We can't just say a single value. It's much more than a single value. It's a set of points, and the line represents that set of points. Likewise, with linear inequalities, we don't just have one solution. We have a whole bunch of points. In fact, because the way linear inequalities work, we don't have to be exactly on the line. We can be greater than or less than, depending on inequality, and satisfy that linear inequality in two variables. What that means is that we get one entire side of a line, all the points on one entire side of the line, either top side or bottom side, that are solutions to our linear inequality. That's called a half plane. So we're going to get the top half plane as a solution set, or the bottom half plane as a solution set, not both. And it depends on your equation, it depends on your inequality. So the last bit, if you have these, the less than or the greater than, and maybe you've inferred that as I've been talking here, if you have the less than or the greater than, the line itself, the points that make the line itself, that separates your half planes, that those points are not part of the solution set. Let me say that one more time. If you have greater than or less than, strictly less than or strictly greater than, the line itself that separates your half planes is not part of your solution set. We've been exploring that this entire time. Like, hey, that's a line. This thing is kind of based on a line, but it's not necessarily the points themselves. In fact, the points on the line are not even included in this inequality, in that solution set. That's what this said. This said that point's on the line. None of the points that are on the line, none of the points that would equal 15, none of those points would make a solution here. They'd all be equal to 15. That's false for that inequality. So with these two inequalities, the line itself is not part of your solution set. That's weird. With these two inequalities, if I make them less than or equal to, greater than or equal to, then the points themselves are included in the solution set. You still get the half plane, but then it's just the difference of whether you are including the line in the solution set or are not including. So think about that. If you put equal to, it's basically saying, yeah, you have all the other stuff we just talked about from here, but now you're also including that line. So it puts it in there. It says, hey, yeah, so you get half plane and then all the points that are on the line too. That's what the equals part of it says. The equals part says you can be on the line or above it, on the line or below it. These say you have to be above the line or below the line. That's the idea. It's very, very similar to the parentheses versus the bracket idea. These would create a bracket. They would include values. These are going to are going to have a line in the solution set. It's going to say, yes, it's part of it. These would be like the parentheses saying, nah, you're pretty close, you get right up to it, but you can't include the number itself. Same thing here. When we don't have the equal sign, you do not have the line as part of the solution set. So next time, we're going to talk about graphing, but what you can expect is that we're going to be shading here because you're going to have to show what the solutions are. It's not just about the line anymore. I think I beat that to death, but lines we already got. That is a solution set for a linear equation with two variables. Now we're going to be drawing lines as a separator. Whether we include them or not depends on the inequality I give you. We're going to be drawing those lines as a separator. Then we'll be illustrating it really as to what solution set works, the points above or the points below. And we'll be shading half of our graph, either the top half or the bottom half. I'm going to show you exactly how to do that in the next video when we graph some linear inequalities.